everyone. Just today, you know, from the Institute of Space Sciences, we are celebrating as well the Asteroid Day, that is an international initiative that, basically we are celebrating that a huge asteroid about 50 meters in diameter, perhaps a piece of a comet, was disrupting, producing an airburst in Tunguska region in June 30, 1908. That time, you know, and for a very small time difference, this event could have occurred over St. Petersburg, for example. So changing perhaps our vision of asteroid impacts in, you know, in the contemporary literature, contemporary history of our civilization. And we are just celebrating that that asteroid was missing a really populated area in the planet. And at the same time, obviously, after these exciting results by DART mission, we are also celebrating that we have a plan to deflect asteroids, because this DART NASA mission was really exciting and very efficient in deflecting asteroid dimorphos. And today, from the Institute of Space Sciences, we are presenting a really exciting work made with my colleagues Eloy Peña-Asensio and Pau Grèbol-Tomàs, that will be, in fact, presenting today the talk on this huge bolide, this super bolide we call, because it was detected by these US government satellites that are checking the, you know, the nuclear activities all around the globe, but at the same time, they are also detecting super bolides all over the planet and keeping a list of events. On May 18th of this year, we had this huge super bolide over Spain and north of Portugal, and you will be really excited about the origin of this body, as Pau will explain just right now. So welcome to Asteroid Day at the Institute of Space Sciences, and thanks everyone for being here. Yes. Hola. Nos veu, no? Y... Okay. Vale. Okay, so hi everyone. Thank you for coming here. Yeah, as José María said, I am Pau Grèbol-Tomàs. I am a first year PhD student here at ICE, and I will present the results of our study of this amazing bolide that flew over the Iberian Peninsula. And this work has been led by Eloy and José María, as already said. Okay, so every presentation has been made already, so I will start telling you my story with this bolide, if this works. Oh, there's no works. Okay, so it was a nice weekend of May last month, and I took a day off on Monday because here in Catalonia it was a local holiday.
and I was on my vacation trip to Italy, and it was 7 a.m. in the morning, and I was on the bus sitting going to visit the city of Venice, and I was looking at my phone, and at that time in the morning, this it appeared along with this amazing video just from the night before. So yeah. Okay, and I was staring at this video and I thought, okay, it can be really interesting. And just after this video, several other videos started to pop from people who recorded this event from their mobile phones. Just this girl here. Also, these guys who were dancing. And finally, probably the most viral video of this event was this one from this girl, from which the bolide goes just over her head. Really, really amazing. And not only people were amazed by this phenomena, also animals were. See these ducks, for example, who were drinking water and then became astonished when night became day for just a moment, and they didn't know what was happening there. Okay, and just the day after this event, several newspapers started to make news about this event, and there were several theories about what this could be. You see here, for example, Reuters, Catalan newspapers, German, Portuguese, well, French, El País, those from New York, Portuguese newspapers, even Galician newspapers. So it was a massive social event. So one of the aims of this talk is to give a comprehensive explanation of what this thing that we saw on the sky could be. When we encountered these events, these bolides, we start with the theory that this is a rock that came from space, and due to the friction with Earth, it starts to glow. And due to this glowing, we see this amazing fireball event. But we want to guess where this rock may come from. It comes from outer space, but it could be from two main sources. It could be a rock from an asteroid or a rock from the core of the comet. As a reminder, I will tell you about the differences between these two bodies of the solar, these two type of bodies of the solar system. Asteroids are kind of big rocks that live in this region. We lose the latter, it's more professional. Which live in the region between Mars and Jupiter, which is known as the main asteroid belt. And these bodies are mostly rich in silicates, but there are also which are really rich in iron, nickel. There are different types of asteroids, which is not anything that is special for this case. There are different types of asteroids of their particularly relevance. And these bodies do not show any kind of activity. I will tell you about this in a moment. Regarding the comets, these objects live in the outer solar system, in an orbit which is farther than the orbit of Neptune. And these objects, for living so far from the sun, they have kept water and organics on their holes. So this means that when, for any means, this rock approaches the sun, it starts to heat up, and this heating makes the water to sublime and become gas. And this is what we see in comets as a coma, a gas that is involving the rock, the main core. And this is what we say that is the activity. The activity of a comet is the gas that is being released when it is approaching the sun. And asteroids, most asteroids do not show any kind of activity, where there may be some asteroids that may do, but their general trends are these ones. Okay, so now we have a rock of any kind that is spinning around the sun, and something happens that makes it to collide with Earth. What could this be? So there are three main phenomena that may lead to this collision with Earth. The first one would be gravitational perturbations, which means that imagine that we have our asteroid or comet spinning around, and it encounters a massive object such as Jupiter or Neptune, and this makes this asteroid or comet to destabilize of its orbit and fall into the inner parts of the solar system, where the Earth and us are. The other thing that can happen is that unlikely two asteroids or two comets may collide, and this will eject several debris into the solar system, and some of these debris may encounter finally the Earth. And the last phenomena that can happen is tidal or degassing disruption. This is quite more tricky. Imagine that we have a body that is approaching the sun, which may be here, and while approaching the sun, there will be some differences in the gravitational pull that is being held by the different parts of the rock. So this side of the core will be more pulled into the sun than this other. And if this tidal force is enough, it can break up the rock, the comet or the asteroid. And concerning the degassing disruption, it will be particularly similar considering the case of comets. When the comet approaches the sun, it will increase its activity. It will release more gas and will be releasing more gas. And this gas can disrupt and break the rock, ejecting several debris, and some of them may eventually reach Earth. Okay, so this is what we now we have a rock that is reaching Earth, and what do we see? We can see this object from different points of view, but the first one would be from space. We have plenty of satellites that are orbiting Earth, and these satellites are not usually designed for observing superbolides, but some of them may be able to. For example, this is the example of the lightning imager on the Meteosat third generation satellite. And this lightning imager is designed to observe lightnings, and lightnings usually appear as single dots on the Earth's surface. But in this case, these imagers saw a very rare lightning, which was comprised of several dots of different intensity. So this would be a proxy of our trajectory of the bolide. So it occurred over the northernmost part of Portugal. And the other kind of detection that we can make from space is those from the United States government sensors. These government sensors are designed to observe, as Josep Maria said, nuclear lightning, nuclear flashes over the Earth, but it can also be used to observe superbolides, shining events from these rocks from outer space. The results are made publicly available by the SNEOS webpage, which is held by NASA. And astronomers use these data to study different events that happen all over the world. But there is some disagreement about whether these results are truly reliable or not, because as you see here, or no, here, okay, as you see here, these are two events, the Calamity event and the Bird Bay event. The dashed line corresponds to the orbit of the Calamity event with the values that SNEOS gives to us astronomers. And you see that the dashed lines does not match with this solid line here, which would correspond to the orbit based on ground-based measurements, as we do from Earth. So in this case, it would be a completely mess to rely on SNEOS. But on the other case, we can have cases like Bird Bay, in which you cannot see this dashed line, and this is because it perfectly matches. It overlaps with the solid line, which is the true orbit of the event. So, okay, how reliable are these events is kind of a question. In our group, okay, no, in our group, no. Okay, we can see here the webpage of SNEOS and which data can we have from this USG satellites of this event. These are the parameters of latitude, altitude, velocity, and the total radiated energy. And look here, we have our event. Yeah, we can use this CNEOS data to study our event. And in our group, we have studied, we have made use of the CNEOS webpage several times. On 2021, these CNEOS data were used to calculate the trajectory of an event that was only partially seen from the ground-based stations. And in 2022, all the values from CNEOS were characterized using several orbital parameters. And lastly, in last year, this comparison was made between CNEOS values and those from ground-based observations to see if there was an event such as calamity or the other one that I showed you before. So we can also observe these kind of events from the ground, not only from space. And from the ICE, we manage all the data that is gathered by the Spanish Meteor Network, which is a program collaboration that has plenty of cameras spread all over the Spanish territory. And this aims to monitor the sky, and we take these videos from this camera of our collaborators to make the studies that I will show you, I will present you in these next slides. Okay, so this event, of course, was recorded by our stations, and we baptize it with this cute name. And I will show you the 4 videos that we have used to study the SPMN 180524F event. This is the camera video from STEPA. You see the bolide going over there. And note that STEPA is here in the southernmost part of Spain. And as we saw on the meteosite video, this event happened over here on this region. So this quite a far event, but it was still detected by our camera. It was also detected by our camera from Navianos de Valverde, which is closer to the event, so it will be brighter, as you see here. And still, we can see that there is this persistent glow after the bolide has passed by. This event was also seen from Sanlúcar de Barrameda, which is also in the southernmost part of Spain. But this video is really nice because you can see all the trajectory of the bolide. Okay, and finally, the last camera that reported this event was the camera which is held by ISA from Casas de Milan in Extremadura, over here. And you will see the event going, yeah, the bolide going. Okay, so this is quite a really bright event and really interesting for science, as you will see. So our goals in this project is, as I said, to compare our ground-based measurements with those from the CNEOS webpage to test whether these values are truly reliable or not. And the second one is to give a comprehensive explanation about this event and its origin due to the social media impact that it had. And maybe to assess the question as if there was any meteorite, could it be recoverable or not? So first of all, I will talk you about the methodology that we have used. So we have a camera, we have our camera, let the station A, and our camera sees the bolide going on that direction. And we can know at which altitude and azimuth coordinates the bolide goes by in local coordinates. But yeah, this is the local coordinates and is quite a problem. So this is the recipe of our plane intersection method. We go from these altitude and azimuth coordinates to a global coordinate system that will give us this apparent trajectory according to the celestial sphere. And we do this for station B and station A, and we can get these two apparent trajectories. And the next thing that we do is to build the plane of sight. This plane of sight would be these shadowed regions here, which is the plane that involves the apparent trajectory and the station. So we have these two planes of sight, and the third thing that we do is to combine these two planes and trying to see at which line do these planes intersect. And this would be the real trajectory of our bolide. Okay, so with this, we can exactly know from the altitude and azimuth of at least two stations, which is the trajectory. But there is something that I have missed in this explanation. And the thing is that when I came back here at ICE on Tuesday, before going on vacation, I did not witness the events. So what I had was only videos. And from videos, you cannot directly know which is the altitude and azimuth. What you measure is pixels, pixel scale, not altitude and azimuth. So we need to make some conversion from pixels to altitude and azimuth. We need to know this pixel here, for example, at which altitude and azimuth does it correspond to properly build the trajectory from each station. So the thing is that this calibration, this camera calibration to make this conversion is not trivial. Because as you see here, these are different types of cameras, and you see that the horizon is differently blended on each camera. So we need to perform this calibration individually for each camera. And for the first time in our group, we have used this SkyFeed 2 program, which is a really nice program that relies on the skies on the background to make this feed of the of the shape of the camera. It takes into account the optics of the camera and blends the different the celestial grid to match the position of the stars. And with this, we can know a relation between pixels, pixel scale, and altitude and azimuth. And okay, now that we know the trajectory, we can start to derive different parameters of our body. The first one would be meteorite density. This picture here shows the moment of maximum fulguration as seen from the camera from Sanlúcar de Barrameda. You see that these red dots would correspond to calibration stars, and these pink pixels here are saturated pixels corresponding to that moment of maximum fulguration. So at that moment, we can compute the tensile strength. Tensile strength is the maximum pressure that the meteorite can hold. And it is measured at the moment where the meteorite breaks up, which is the moment of maximum fulguration. And it's computed with this really nice and simple formula in which this rho here corresponds to atmospheric density at the point of maximum fulguration, and this B corresponds to the velocity of the meteorite at that moment. And finally, knowing the tensile strength, we can compute the meteorite density with this semi-empirical formula. And okay, another thing that we can try to measure is the meteorite mass. Meteorite mass is quite interesting to know if you want to recover some meteorite. We build these plots of velocity and height. And you see that these points from here corresponds to the measured values in each station. And what we do is to make a fit to this equation here. And this fit, which would be this blue line, would allow us to recover these parameters alpha and beta. And these two parameters are a dynamical model that relate these alpha and beta with the initial mass and the final mass. So this dynamical model allows us to know these two values. And yeah, the thing is that height in this plot comes from highest altitudes to lowest altitude. So it goes on the other way, it's flip the x-axis. And note that at the initial points do not change the velocity. And this is because the atmosphere of Earth is not really thick. It is not so dense to make an acceleration to occur in these dots. Whereas it can happen at lower altitudes. Okay, so Now I'm going to show you the results of this. I have divided the results into main parts according to the two goals that we have. The first one, we will compare our results to the USG values. And the other one, we will try to guess what is the origin of this event. So here you have as a reminder the table of all the parameters that are given by the CNEOS webpage. And with these two formulas, we can calculate the initial mass and make an estimation of the initial mass and the meteorite density according to the USG values, assuming that all the radiated energy was initially kinetic energy. We can compute the initial mass, and as these values from here are measured at the moment of maximum fulguration, we can estimate the meteorite density as I said before. So, okay, so these are the results in this table. We are particularly happy with the results. There is quite a good match, at least for these physical parameters. The other thing I would notice from here is that our uncertainties include the CNEOS values on the uncertainty rate. So we are quite happy with these values. And this event was special, as you will see later. And we started to hint it because we started to hint it with this plot of height and velocity, where we compare our event, which is here, with all the events from the CNEOS webpage. You see that this event is truly special because it occupies a region which is not occupied by any other event before. It has the highest altitude in the database. It is the 5th fastest with respect to Earth, and is the 4th with lowest density. So this makes this event quite exceptional, as we will also see later. We can also try to compare our trajectory with that related to CNEOS. Here I show you the true velocity and height plot of this event. These scattering points corresponds to the points measured by each station, and this yellow line here corresponds to the velocity feed plot. We are completely sure that we're truly sure that this value is quite correct of velocity because we have merged this alpha beta model with the radiometric measurements from the CNEOS webpage, and you see that the velocity feed does this velocity line does not change. There is no change in the slope. So this means that the bolide does not decelerate, and this is okay because this event happens at high altitudes, and at these altitudes, as I said, density is not so high to make this density to change, this velocity to change. Sorry, and what we also have here is this gray line here, which corresponds to the photometric. This is the count of the number of pixels, of bright pixels, that appear around our meteoroid. And you will see here this bright peak corresponding to the moment of maximum fulguration, and these subsequent flashes that would be represented by these other jumps. Finally, we have here these, there are two lines here. I don't think if you will be able to see it, but one is the energy peak as seen by our ground-based observations, and the other one would be the peak as seen by the CNEOS or the USG satellites. And you see that there is quite a good match, so we're also happy with this. And finally, we have this dynamic strength. Dynamic strength is computed with the same formula I showed you before, and says which is the maximum pressure that is being held by the surviving fragments of our meteorite. So it means that the last fragments that we saw over here are suffering a pressure of 1 MPa, which is also quite high, meaning that this rock had really strong minerals on it. And then, according to the trajectory, we can also try to compare the numerical values of our trajectory with that from the CNEOS webpage. According to the longitude and altitude, the position of the event, there is quite a slight change in the position, as you will see later, and is also depicted here. And note that Cineos values are not so precise as ours values, which is quite okay because this event remind that is measured from a satellite hundreds of kilometers from the surface of Earth, and we are measured from a closer point of view. The thing on this slide is that there is some differences in the slope and the azimuth of our event. But maybe to see it, we can also see these values plotted in a three-dimensional plot. Here we have the full trajectory of this event. The event started over the Extremadura region, or yeah, under Andalusia. No sé, I don't know where is the frontier exactly, but the thing is that it started at 133 kilometers above the mean sea level and ended on over the Atlantic Ocean at 54 kilometers above the mean sea level. So should it have produced any meteorite, we will not go for it because it would have landed on the sea. Then we have here these the four stations along with their planes of sight that I showed you before, that depict which slice of the full trajectory these cameras had seen. And we have these two dots here. This red dot, corresponds to the position of maximum fulguration as seen by our ground-based observations, and this pink dot here corresponds to the moment of maximum fulguration, but seen from the satellites from the USG sensors. And okay, so maybe to better visualize this, we can look at this nice animation. You see here, these lines correspond to the apparent trajectory as seen from each station, and this zoom allows us to see the full trajectory in 3 dimensions. Really nice. Note please that the pink and the red dot do not appear at the exact position. There is a slight change in the position of the bolide, but we are also quite happy with this because this is not the calamity event that I showed you before. Now that we know the trajectory, we can also try to guess what was the orbit of this event. That will tell us where this did came from. Okay, so we have here the comparison, as I said before, of our orbital values. We have calculated these orbital values using the rebound and body numerical integrator. So we have taken the initial velocity of our meteoroid, which was this vector here, for example, and then we have put it backwards and integrated with time backwards to see whether this came from. This rebound takes into account different gravitational interactions, and with this we know that this was the orbit. So we are quite happy also with the results. There is some slight change in the inclination and the semi-major axis, comparing the Cineos values with our values. And to put this in context, because these numbers may be difficult to read, we also have this nice plot here in which we have the different orbits of the planets, the main asteroid belt, and here the pink orbit corresponds to the orbit according to the velocity values that were given by USG data, and the yellow region corresponds to our orbit. So, okay, there is quite a good match. We are also happy with this. Remember the calamity event, this is anything like this. And to see this in 3 dimensions, we also have this another nice video. You see here the differences between the slope, the inclination of the orbit, but there is quite a good match between both orbits. Okay. So now that we have explained and we have compared our values with those from the USG, we can also try to guess what is the origin of our rock. We have compared our event with the 824 events of the European Fireball Network. This is a massive database, and we when we compare the final height and the initial height of our meteoroid, we see that our event is clearly an outlier. It does not occupy any region of the bulk the bulk of the events that were recorded by this network. And this may be because the largest mass in the catalog is nearly 100 on this database, and our event is more than half a ton of mass. Maybe there's some bias according to this mass shift. We can also try to compare our event with these two parameters, the pressure factor and the decision parameter. The pressure factor is a value that evaluates the dynamic strength. Just remember that this dynamic strength is the maximum pressure that can be held by our core. And the decision parameter is an orbit invariant that is used to classify the different orbits. So our event is classified as PF2 according to the pressure factor values, and is falling in the region between in the JFC, which means Jupiter family comets. We see nothing special here. It seems to behave just like other events, and these JFC comets are comets that were formerly living in the Kuiper belt and then started to go into the inner solar system, and then were captured by Jupiter and started to orbit in particular orbits that are related to Jupiter. So, okay, the next thing that we can do. Oh no. No. Okay. The next thing that we can do. No, I will not touch it anymore, I think. The next thing that we can do is to compare our event with eccentricity and semi-major axis. We also have here all the values, all the dots that corresponds to these 800 events from the Fireball network, European Fireball network. And our event lies in this shaded region which will correspond to Jupiter family comets. And it has a behavior similar to PF1 and PF2 events. So, okay, it is according to the other plot that I showed you before. So maybe we can assume that it had a cometary composition. And assuming that it had this cometary composition, we must take a look at this value here. This is the value of the perihelion. So this is the minimum distance between the meteoroid when it was on its orbit and the sun. And this value is really, really tiny. This is really, really small. So this means that should it have a cometary composition, this object could not have lasted so many revolutions, because every time it went around the sun and close to the sun, it would have lost more and more of its mass, and eventually it would have disappeared. So this would be, if it had a cometary composition, quite a young event. So we see that it falls in the Jupiter family comet region. We have also worked with people of the NEOMOD project, which is a computational model that takes into account plenty of gravitational interactions. And they have told us that this was a Jupiter family comet with 100% confidence. So everything is clear, everything seems to fit. So we can say that the origin of this event was a Jupiter family comet. So we are happy with it, and we go back home really happy. Or not. Plot twist. The thing is that when we compare our values of density, they do not match that of comets. We would expect that a comet should have a density of about that of the water. But what we see is that our object has a density much higher. And this density is more similar than that density observed by asteroids, not comets. So this is quite an issue to say whether this may come from. There may be some relations. There are studies that relate asteroids and comets, but still there is a long way to try to relate these both types of objects, asteroids and comets. So this is quite an issue, and we cannot truly say that this was a Jupiter family comet because, yeah, density does not match. So we reach the conclusions of this work. Comparing with the USG data, we are quite happy with these values. Our values match with those from the USG sensors. And comparing with other elements, we have worked with different hypotheses. One hypothesis would be that this object may be a Jupiter family comet, but during its lifetime, it may have encountered some other objects that may have collided with it, and this would have smashed the core of this comet and increasing its density. So that would explain such anomalous density. Another thing would be that it would be an asteroid that may have moved to a Jupiter family comet due to any gravitational interactions that may have happened. And there are several other hypotheses, such as that they may be a sun grazer comet. That means that it may be a comet that really approached the sun really, really close, and then due to this degassing disruption, it may have breaked up, and this debris, one of these debris, may have reached directly the Earth. So we do not surely know what is the origin. It may be an asteroid, a comet, and we are still debating what this could be. And we are analyzing, trying to analyze more data, trying to find more colleagues to analyze it. And please, if you want to find more information, we think that we will publish the paper really soon. It's already submitted. So please go stay tuned and go check it. So that's all from my part. Thank you for your attention. And I would not like to end the talk without acknowledging all the people that gather all the camera videos and send them to us, all our collaborators in the Spanish Variable Network. So yeah, thank you to all of them and to all of you for listening to me today. Thank you so much. I don't know if there is a question. Yes, please. Mm-hmm. Okay. I would say that this is not one of the heaviest events. Okay, let me go back. Oh. Mm-hmm. Oh. Okay. We'll show you the plot of the CNews webpage, in which they have reported the brightest events of all of them, of all that were recorded by the webpage. A ver. Okay, here. Remember that we have computed the density, and we have used this value to compute also the mass. See here that our event is nothing unusual according to the impact energy. There are more events with more energy that were measured by the CNews value. So I would not say that this one of the most massive events that have reached Earth. Maybe it is one of the brightest and massive ones seen in the Iberian Peninsula. This could be true, but I will not say it's not the best of the world. Yes, as was an asteroid. Yeah. Yes. Yeah. Maybe you are referring to the comparison I made with the 800 database values. Meaning no. For example, this plot here. In this plot, we compare our event with the events from the European database. These events covers the usual events that we see. We are presenting here one of the best events that we have here in our network, but we have events mostly daily, and these events would lie here. in this region with less masses. And yeah, the thing is that this event is special in the context that is unusual, but putting in context of all the lifetime that meteorites have been measured, it is not really I don't know how to say it, because it's special but not so special, to be honest. It's more special about its origin and the discussion of its origin, not the thing that people saw.
To put an example, it's like here we have events that are much smaller than our meteoroid. So it's like you want to compare apples, oranges, you have a sample, that perhaps has been going over the solar system, and as well accreting some of these apple and oranges over time. So it goes with a huge mass, and even to the slope, the luminous trajectory was very unusual, was 500 kilometers, 550 kilometers long, because of the slope of 10 degrees, according to the data. So obviously, the event is not comparable to this set. Perhaps when we can study much of this superbolide also from space with enough accuracy, then we can get additional, data in that part of the plot, and then we can say more. That's the topic here, you see, 200 kilograms. So everything there is small, relatively small in comparison to this.
Any other questions? I don't know if there is any question in the chat. No. Any other question? Maybe. Oh. So we leave it here. Thank you, all of you.